Well, welcome to the problems at the end of chapter 3. So you'll see we're section 3.8, the problems for the end of chapter 3. Just a quick run through how these problems are now going to work. You'll see this is obviously question 1 that is in front of us, and question 1 has been broken up into 7 separate bits. Really, question 1 is asking for the Sauter mean diameter of a powder. So the real nub of the question is part 5, and as always when obtaining a flow type result from flow equations, a good idea is to check the Reynolds number, or in this case the modified Reynolds number. So part 5 and part 6 are equally relevant to calculate the Sauter mean diameter, and then to demonstrate that the equations we used in that calculation are valid, because there will be in fact laminar flow equations. But you get the idea. The problem is being broken up, deconstructed into its separate sections in order to help you work through the problem, rather than simply say, here's all the data, now go away and calculate the Sauter mean diameter. So we've done the decomposition for you. Another trait within the fundamentals book, which I'd like to just say something about, is what's on the right hand side here, the little box that you see here. And I think the best way of doing that would be to remove me for a while. So okay, here we have the equations that are going to be useful in the solution of the problem. First of all, we have a laminar flow equation. That's the Kozeny-Carman equation. Fair cop is missing a minus sign, but we're just interested in the numbers that are going to come out of it, rather than the fact that the pressure gradient, which is what this is acting in the opposite direction to the velocity. So there's two vector quantities, pressure gradient and velocity, and the minus sign simply balances those up. We don't need that because we're just calculating values, effectively a scalar. And then here is our modified Reynolds number equation. Both of those equations are needed in question 1. The Carman correlation is needed in question 2. That's later here. But this is a typical way that we formulate problems in particle technology book, the fundamentals of particle technology book, where the equations that you need, rather than go scooting back into the chapter, or worse still into other chapters, the equations that you need are by and large within the same within the little box out next to the problems. Okay, so it's designed to try and make life relatively straightforward when answering a problem. So rather than answer it in Word, let's now resurrect me, so to speak, and go back to the whiteboard, which has the problem with some space in to enable us to do some calculations. Okay, so a powder is contained in a vessel to form a cylindrical plug 0.8 centimeters in diameter and 3 centimeters long. Well, of course, the logical thing to do first is to draw a diagram, and it doesn't have to be a great diagram, it won't be, but it's something that enables us to conceptualize what's going on. So here we go. Here's our plug of powder. We're told that this is 3 centimeters long and 0.8 centimeters diameter. Okay. Not very good at drawing arrows, but you get the idea. What else do we know? We know that the mass of the powder in the plug is equal to 2.2 grams. 2.2 grams. And we know that the density, and I'll use rho s for solid density, solid density is 2.5 grams per centimetre cubed. Let's call that mil. It's the same as centimetres cubed, but easier to write. We can carry on in centimetre gram seconds units, CGS units, because we're in centimetres, that's centimetres cubed, grams, and the third inherent unit is that of seconds for time. So we use CGS. There's no point converting this to SI for reasons that become apparent if they're not already. First of all, we need to know how to convert between mass and volume. Well, density is equal to mass over volume. You don't have to remember that. All you have to do is remember that the units of density normally are kilograms and meters cubed, kilograms per meter cubed. So from the units, kilograms per meter cubed, clearly that means density is kilograms mass divided by volume meters cubed. So you don't have to remember this equation, it just comes naturally from the units. A little trick that's useful in lots of simple equations. So if we want the volume of this powder down here, and I know we don't, we want the volume of voids, but let's work on the volume of the powder to start with. So volume of solids, we know it's going to be the mass divided by the density. Volume is going to be the mass divided by density, having just rearranged that equation there. So that's mass over density, and that gives us, in terms of numbers, the mass is 2.2, density is 2.5 grams per mil, 2.2 divided by 2.5, and that will of course be in centimetres cubed, or millilitres if we're going to use a simple unit. Now, the volume concentration of solids, that's going to be the volume of solids divided by the total volume of this porous media of the bed. We know that the volume of solids in the bed is whatever this happens to be, and if we divide by the total volume of the bed, then that gives us the volume concentration of solids. So let's put that up here. So volume concentration of solids is going to be well, the same as we had before, 2.2 divided by 2.5. We've not worked that out yet. So that's the volume of solids, and now we need to divide by the volume of the bed, which is going to be pi, because it's circular cross section. The area of a circle is pi d squared. Okay. And to get the volume, we need the length. So we're pretty much getting to what we need now. And of course that's dividing the volume of solids, which is what we have here, by the volume of the bed. Right, might need a little bit more space, so let's draw that up a little bit. Keeping it visible, that'll do nicely. Okay, let's bring the question down to here then. So we have 2.2 divided by 2.5 pi over 4, so we can actually take the 4 up to the top. D squared is 0.8 centimetres, which of course we need to be squared, and L is the 3 centimeters length. So basically that is what we've got. So if I go for my trusty calculator, it's a very basic calculator, but it doesn't need to be any more sophisticated than that for this. 2.2 divided by 2.5, okay, is 0.88. So that's the volume of solids that's in the bed. If we times that by 4, divide by 3.142, divide by 0.8, divide by 0.8 again, divide by 3, 0.58. So that gives us the value of 0.58. 0.58. That's the solids concentration, and basically the solids concentration, the amount of solids that's present in the bed, plus the amount of voids in the bed, otherwise known as the voidage, and also the porosity, sums up to 1, to unity. So in your porous media, in this bed over here, you've either got solids or voids and nothing else, and we know it's 58% solids, so therefore the voidage or porosity is 42%, or 0.42. So the answer to this particular part of the question is B, 0.42. That is the porosity of the plug of powder in the bed. Okay. So the next question is to work out the pressure drop. We're given some physical data, some of which we're going to need for a later question, later part of the question. What's the most relevant bit that we need? Well, we don't need the 6.6 centimeters cubed per minute currently, because we're being asked to calculate a pressure drop, and for the purposes of calculating the pressure drop, what we need to know is the height of the mercury recorded on a manometer, the density, only we're being given the specific gravity, but that's the density of something divided by the density of water. So the density of mercury that we're going to use here is 13,600 kilograms per meter cubed, and we better go back to SI units now because we want a value in pascals. The thing I didn't mention previously is that porosity or voidage is dimensionless, so it doesn't matter whether you're SI units, CGS units, imperial units, that voidage will be the same in all those different units because it's dimensionless. But that's not the case here. So what equation do we use to convert between pressure or pressure drop, which is what we want, and height of mercury? Well, that's simply depth times density. Sometimes we might call that H rho G, not rho S, so it's not the density of the solids, it's the density of the fluid, so I'll just call that rho rather than rho F. There's no need. Rho on its own is density of the fluid, and G. So fairly straightforward calculation, this one, because H is 0.06 meters, that's 60 millimeters, okay, 0.06 meters, which is 60 millimeters, times by 13,600, better not put a comma in, 13,600. Where do we get that from? Well, that's the specific gravity times by 1,000. You know, specific gravity or relative density is the true density divided by the density of water, which is 1,000. So actual value of density is 13,600. And then it's very tempting to use 10 rather than 9.81. It looks to me, if you had used 10, then clearly you'd lose 2 noughts there, get a 6 there. That would be 6 times 136 times by 10. it's clearly looking like it's going to be 8,000. Better just check that. 0.06 times by 13,600 times by 9.81 is indeed 8,000 pascals. Okay, so the pressure drop when we suck or blow air at a rate of 6.6 centimeters cubed through that porous plug in the part 1, the pressure drop that's measured in a manometer, that's just a simple two tappings either side of the bed, and looking for the difference in height of on the surfaces of the manometer, gives us 60 millimeters rather, which converts to an SI pressure of 8,000 pascals. So we're getting to the bits that we need for the Kozeny-Carman equation. So we know what the voidage of the bed is, or the porosity of the bed. We know what the pressure drop is. We know what the bed height is. We now need to calculate the superficial velocity, and that's really a conversion from 6.6 centimeters cubed per minute into SI units, and then from the volume flow rate into a velocity. So what we're starting with is that Q, the volume flow rate, equals 6.6 centimeters cubed per minute. So we better watch out here. I think the safest thing to do is to do that as a conversion first. So we know we're going to have to convert it into seconds. So we know we're going to have to divide by 3,600. And to convert centimeters cubed into meters cubed, it's 100 times 100 times 100. So that's 10 to the 2 times 10 to the 2 times 10 to the 2, or 10 to the 6. Only, of course, we're not pumping massive amounts, meters cubed. It's the opposite. It's minus 6. So that's 10 to the minus 6. That's 6.6 times 10 to the minus 6 meters cubed divided by, better correct that, divided by 60, because that wasn't centimeters cubed per hour, it was centimeters cubed per minute. Sorry about that. That makes the calculation a little bit easier, because that now gives us 60, which of course is 1.1, and then times 10 to the minus 7, because we're dividing through by 60, not just by 6. So that was a relatively straightforward calculation. The next bit is a little bit more complicated, because we have to use continuity. We know that the volume flow rate is equal to the cross-sectional area times by the velocity. Okay, and we actually use U0 for superficial velocity, so I'll use U0 here. And that's the continuity equation. What goes in comes out, effectively, is what that says. So if we want U0 and we know Q, because that's what we have down here, then we need to work out the cross-sectional area, okay, of the bed. Well, that was, or that will be rather, pi d squared over 4, just as it was in the previous calculation. So that's the cross-sectional area, which is pi 0.8 squared over 4. And if we want U0, U0 is going to be equal to Q divided by A, Q divided by A, which is equal to 1.1 times 10 to the minus 7, all divided by pi. I'll correct between centimetres and metres in a moment. Let's just stick with 0.8 down here, squared for the moment. Bring the 4 up to the top. Now we have to correct for the diameter, because this 0.8 should actually be 0.8 times 10 to the minus 2. So we're squaring it, so that's 10 to the minus 4. So in fact, we are timesing by 10 to the 4 here. That's part of our conversion of units from centimetres to meters, or if you like centimetres squared, which is what this area calculation would give us, into meters squared. Seeing as we're dividing by the area, then clearly we need to multiply our answer by a rather large amount to make make that conversion. I think it's calculator time again. It's not too difficult a calculation. I won't bother with any of the powers yet. So that's 1.1 times by 4 divided by 3.142, more or less, divided by 0.8 divided by 0.8, which gives us 2.2, which gives us 2.2. Oops, let's come back down here. 2.2. Now we've got to sort out all the tens. So that's now times 10 to the minus 3. Times 10 to the minus 3 meters per second. 2.2 times 10 to the minus 3. So that looks to me like it's answer A. 2.2 times 10 to the minus 3. Good, good, good. Looks to me like we're ready to do the Kozeny-Carman calculation, which is going to be a little bit more complicated. So first off, we better get the Kozeny-Carman equation back. So the Kozeny-Carman equation is basically Darcy's law, but with the permeability expanded out. I won't bother with the minus sign again. I'll put the equivalent for what permeability is all inside the brackets here, and what we have is 1 minus the voidage squared, specific surface area per unit volume squared, and then we have the voidage cubed underneath. I'm coming back to what's missing from just there in a moment or two. So that gives us the correct units of permeabilities, because that's meters to the minus 1, so that'll be meters to the minus 2, so we've got the right units of permeability. But there is a constant, and that is the cause of a lot of contention. It's a constant, but it's not really a constant, it's more like a coefficient. It has various values. The book value is 5, but it could be other values from 5, but we're going to have to use 5 because we're not told anything else. So the default value, Kozeny constant, is 5. And then Darcy's law simply has a superficial velocity at the end here. So this here is inverse permeability, what's inside the brackets. So that's our laminar flow equation for fluid flow through porous media. Now we need to put some numbers in. We know that the pressure drop was 8,000 pascals. We know that the bed length is 3 centimeters, so that's 0.03 meters. We're told here to use a density of 1.8 times 10 to the minus 5 Pascal seconds, that's SI unit. Inside the brackets we have a Kozeny constant of 5. We then have 1 minus 0.4 1.42, so let's write it out rather than do the calculation. 1 minus 0.42 squared. Then we have the specific surface area per unit volume, which we don't know. That's what we're going to have to rearrange this equation for. Down here we have 0.42 cubed. Okay, and that's the end of that. And then finally we have the superficial velocity, which was 0.0022. I feel the need just to go and check that I've got porosity correct. And velocity 0.022, that's right, 8,000 pascals, porosity 0.42. So if we come back down again, that's a lot of working out to go through. Clearly we need to rearrange that equation for SV, and most importantly don't forget to square root. So SV equals, I'm going to make my life a bit easier because I've already popped this into the Excel spreadsheet. So what we have here is delta P over L, 8,000 divided by 0.03. Just here, whoops, sorry, just lost the transmission for a moment. So going back to what we were saying, that's that is our 8,000 pascals divided by 0.03. That's the all the other items that are in our Kozeny equation. I think I called this density actually when I was talking about it earlier on. Sorry about that. Obviously it's not density, it's viscosity. So the viscosity of air is 1.8 times 10 to the minus 5. Then that's our 1 minus the voidage squared. 0.0022 is the superficial velocity, and then that's our voidage cubed, all calculated. So that's what everything is, the left hand side divided by the right hand side. So that value there is in fact SV squared, and that gives us a value of SV, because we need to take the square root, of near enough 5.5 times 10 to the 5. So what we have therefore is for SV, oops, if I come back down here, so what we have then is a value for SV equal to 5.5 times 10 to the 5 meters to the minus 1. So that's meters squared per meter cubed, which, if I can just scroll back down again, is answer C. I've just circled that already. So that's our specific surface area per unit volume. So the next question is to obtain the Sauter mean diameter. And the Sauter mean diameter is the equivalent spherical diameter for a sphere that has the same specific surface area per unit volume as the distribution. So I'm going to use x for particle diameter again, but this is x with a space in the middle rather than the x that looks like a multiplication sign. Okay, so we need the surface area of a sphere, which is pi x squared, and we need the volume of a sphere, because that's the surface area of a sphere, and we need to divide by the volume of a sphere, which is pi over 6 x cubed. And by the time you cancel the pi's out and two of the x's, that gives you 6 over x. So SV, the specific surface area of a sphere, is equal to 6 divided by its diameter. Okay, and we're told that the specific surface area of the material is 5.5 times 10 to the 5. So x is going to be equal to 6 divided by 5.5 times 10 to the 5. That's going to be 1.1. 5.5, 6 divided by 5.5 is 1.1. So we know that's going to be 1.1 times 10 to the minus 5. And if we're going to convert that from being meters, which is what we're currently in, into microns, we need to multiply by 10 to the 6. There's 10 to the 6 microns in a meter. So that's now microns. In other words, that becomes equal to 11 microns. So the Sauter mean diameter for this powder, the equivalent spherical diameter that represents the surface area per unit volume of the powder, is 11 microns. So that would be the value to use. That would be the value to use in design calculations for fluid flow through porous media, pressure drop, and similar sorts of things. But we're by no means finished, because we need to check that the Kozeny-Carman equation is valid. And whenever we have a flow problem, we have to decide, is it laminar, is it turbulent, and we go for a Reynolds number to help us with that decision. So a Reynolds number is always the ratio of inertial and viscous forces. That's generally true. In our porous media, it's going to be a little bit different from the flow Reynolds number down a pipe. Most engineers can remember that the Reynolds number in a pipe is du rho over mu. Du rho over mu, where rho is the density of the fluid and mu is the viscosity of the fluid. Well, what do we mean by d? Well, that's normally internal diameter of a pipe. Here though, in the porous media, we need some equivalent hydraulic diameter. Okay, so we get that from the volume of voids that's open to flow. So that's the length of the bed divided by the multiplied by the cross-sectional area times by the voidage. So that is the meters cubed volume of voids in the bed. And then what about the solids? Let's take into account the presence of the solids. So it's the solid's surface area, because that is now the volume of the bed times by the solid's concentration. So that's the solid's concentration. That's now the solid's volume inside the bed. That would be meters cubed of solids. And if we multiply that by specific surface, that gives us the surface area. That now is in meters squared surface area of the solids. So that is our equivalent hydraulic diameter. It's the volume of voids open to flow divided by the surface area of the solids. And clearly we can cancel out those terms there. So that's our hydraulic diameter. What about U? Here, for velocity, we really mean the velocity within the pipe, or the interstitial velocity within the bed, because that's the equivalent of having a pipe. Now, the conversion between interstitial velocity and superficial velocity, which is typically what we measure with a rotameter or a device, because we measure the velocity of the flow coming into the onto the surface of the packed bed. That's what superficial means. It's on the surface of the bed. That is the superficial velocity divided by the voidage is the interstitial velocity, and that gives us something else we can cross out. So that just leaves us now with the density of the fluid divided by the viscosity of the fluid. and that's the density of the fluid. It doesn't matter what the solids are. There could be steel ball bearings or ping pong balls. If they're a certain size, they'll have those two things will have the same effect on the degree of turbulence in the bed. Doesn't matter whether they're highly dense ball bearings or less dense ping pong balls. For the same size, they'll have the same effect for the turbulence that's taking place in the bed. So it's not the density of the solids, it's the density of the fluid in the modified Reynolds number. Okay, so that's our equation for the modified Reynolds number. So that's equivalent to what we have here. So we have a straightforward equation for modified Reynolds number, which is simply, it's the superficial velocity times by the density of the fluid, 1 minus the voidage times by SV, specific surface area per unit volume, times by mu. Let's put some numbers in there. We decided that the superficial velocity was 0.022. We're told to use a density of 1.2. 1 minus the voidage is 0.58. We calculated that previously. The specific surface area per unit volume is 5.5 times 10 to the 5 meters squared per meter cubed, and then the viscosity was 1.8 times 10 to the minus 5. Quite a lot there, but I think we can still use our trusty calculator. Let's pop that in there. So we have 0.00, oops, let's start again, 0.0022 times by 1.2 divided by 0.58 divided by 5.5 divided by 1.8. That gives us a value of 4.6. 1, 2, 3, 4. 4.6 times 10. 4.6. Whoops. 4.6 times 10 to the minus 4. Clearly we've just cancelled these two out. So the answer is C. Now the threshold for modified Reynolds number, what's the magic threshold we're looking for? We use a value of around about 2000 for flow Reynolds number, and it's not a step change. We just say that below 2000 there's insignificant turbulences to worry about. As you go above 2000 there's more and more turbulences present. In modified Reynolds number terms, the value we use for the threshold for significant turbulence is 2. Not 2000, just 2. So is our modified Reynolds number of 4.6 times 10 to the minus 4 less than 0.2? It's massively less than less than 2. It's massively less than 2. So we're expecting very, very little turbulence inside our porous media. And the consequence of that is that we have used an appropriate equation for laminar flow in order to calculate our specific surface area and thereby the Sauter mean diameter. So the Kozeny-Carman equation is valid in our calculation. And that is question 1 in fluid flow through porous media. Laminar flow using the Kozeny-Carman equation to work out the specific surface area, Sauter mean diameter, and then a check that we've got that we have correctly used the equation for laminar flow. Answer yes. Okay, thank you very much.